Hello and welcome to another lecture of classical motion of a single particle. So, in this lecture we will simply continue our previous discussion on the motion of a single particle in the presence of electromagnetic fields. So, already we have discussed the motion of a particle in the presence of constant electric field, okay, and also then we discussed the motion of a particle in the presence of a uniform magnetic field, but no electric field. Okay. So, that means that we have tried to make two very special case, only electric field and only magnetic field, both are constants. Okay. Now, we will try to discuss the motion when both of them are present. So, just remember that when there is just an electric field which is constant, the particle even it starts from rest, okay, it accelerates and the particle actually has just the particle is experiencing a uniform acceleration due to the electric field. On the other hand, if the particle is just put in a uniform magnetic field without any velocity, then the particle will not experience any force a priori. In order to have a force of nature magnetic, the particle has to have a non-zero velocity. Once the velocity is there, then we have seen that the force which is acting on the particle, if the charge of the particle is q, then the force will be q v cross b. Okay. Then we have also seen that in this way the particle will actually move in a very special way or special fashion, that is in the direction of the magnetic field, uniform magnetic field, okay, which we chose to be the z direction. There is no acceleration. So, the particle actually moves with a constant velocity which is exactly equal to its initial velocity, let us say v parallel or v z, and in the plane perpendicular to the magnetic field the particle actually moves in a circular orbit, and for each component of the velocity in that plane and also for the displacement in each component of the displacement in that plane, we showed that we have a oscillatory solution, okay, simple harmonic type of solution. Then we said that if we combine all these things in the presence of a constant magnetic field, the resultant motion is actually a helix. Okay. So, that means the particle is finally following a helix, okay, whose axis is directed along the magnetic field itself. Okay. So, that means that in the plane perpendicular to the axis of the helix, the particle is actually always making a circular type of motion which we called a gyro motion, okay, or we said that we could also define the gyro frequency and the gyro radius. Okay. The direction of the rotation of a positively charged particle and a negatively charged particle considering gyro motion is not the same, and we actually say I commented about that at the very end of the previous lecture, that the direction of the motion of the particle is in such a direction that the resulting current gives rise to a magnetic field which opposes the resulting magnetic field. Okay. So, you see this is also easy to understand that if the resulting magnetic field should oppose the initial magnetic field, then since we know that the current is actually flowing along the direction of a positively charged particle, but flow of a negatively charged particle, then of course, you understand that those two particles should actually rotate in the opposite direction. So, that finally, the direction of the current is the same and you have the resulting magnetic field direction is also the same, which is always be opposite to the initial magnetic field, initial uniform B. Okay. With that, we discuss today, we start today's discussion where we will discuss the so called drift motion, and this is the simplest of all drift motion, it is called E cross B drift. In this course, I will simply talk about this E cross B drift. I will tell you some names of other drift type of motions. If you are interested, you can of course go through those. Okay. So, here in this case we have one uniform electric field, another uniform magnetic field, and the magnetic field we just say this is along z direction, and the electric field is also uniform and it is also along x direction. So, electric field and magnetic field, they are already perpendicular to each other. So, this is the direction of the magnetic field, which so it is inward the plane of the paper. So, we call that cross field. Okay. So, if it is inward perpendicular, okay, so we denote that by this symbol. Okay. So, we just do this is the for magnetic field, and along x we have the electric field. So, what will be the resultant motion of the particle? So, of course, we know that this will be then q E x x cap plus v cross b, okay, and m v dot. Now, v cross b again I can write like x y j cap, okay, v x v y v z 0 0 b, because b is only along z cap, and I will have x cap will be equal to v y b, okay, plus y cap will be equal to minus v x b, and then z cap there is no component of v cross b. Okay. So, if I have this, I can write q E x plus b v y. So, I can actually, instead of writing E x, I can simply write E. Yeah, E plus v b v y, okay, times x cap minus v x b y cap. So, component wise writing gives us finally v x dot is equal to q by m v e plus v y b, v y dot gives me simply q by m with a minus sign v x b. Okay. I again can take omega g just using this expression q b by m, and I can simply write this is nothing but omega g, and for that actually what I have to take b outside. So, it should be E by b plus v y. Okay. Yes, and this should be actually again minus omega g v x. Okay. Yeah, yeah. So, these two are very important for our case. These two are the governing equations. Okay. What about V z? I simply write V z dot is equal to, once again, is there any force? So, of course, you see there is no force. So, again this is 0. So, V z will be V parallel is equal to constant in this case as well. Okay. Now, I can do something. So, I know this. So, I can take V x double dot will be equal to then omega g v y dot, because this is uniform, okay, and since v y dot is this. So, I can actually have minus omega g square v x. For v y I will have v y double dot minus omega g v x dot, and v x dot is nothing but omega g square E by b plus v y. Okay. And then you can actually write that I have again two equations for, you see, a little bit different, but still they are still controllable, I mean they are still within control and you know how to solve them. So, they are still the equations for simple harmonic oscillation, but this one is direct one. So, you can write V x double dot is equal to minus omega g whole square V x and V y is equal to minus omega g square V y plus E by B, and if you call this one as V y star, then of course you will have here V y star, because this is just a shift by a constant, and you have V y star double dot is equal to minus omega g square V y. Okay. Now, you try to understand one thing, that is, what is the situation over here? The situation is that if you now try to integrate this thing, so they will get integrated and you will have simply, so for V x you will have some quantity, I do not know, like let us say once again some a times, I do not know what I took last time, I can take some V 0, okay, V 0 cos omega g t I can take, okay, omega g t plus alpha, okay, and that alpha I can actually, for the time being I can forget, I can say this is V 0 cos omega g t, and if you have this, then I actually have my x to be equal to V 0 by omega g sin omega g t plus x 0. Okay. The same thing, you see that this is completely very similar to what we got last time, this one. Okay. So, x minus x 0 V 0 by omega g sin omega g t, if you remember. So, this, okay. Then we just called this one as like V perpendicular. Here we are not calling V perpendicular, we are calling V 0, that is okay. Yeah. Then we can actually do the same thing for V y star. So, we can do it for V y star. So, V y star will be equal to again, so V y star dot. So, if you now remember how to actually find these things from this. So, this is your V y star. So, V y okay, I have made a mistake here, it should be V y star, and V y star is this one. Okay. So, I do not have to redefine. So, this is V y star, and if you have V y star, so what I would do, I would simply say that V y star is, okay, I can like do like this. So, V x, yes, so V x dot is equal to omega g V y star, that we can say from here. Okay. So, V x dot is equal to omega g V y star. Now, V x dot we have known, this is now this V 0 cos omega g t. So, it will be V x dot will be V 0 omega g sin omega g t with a minus sign, and that will be equal to your omega g V y star, and your V y will be, V y star will be actually V 0 with a minus sign sin omega g t, okay, and then your final V y will be equal to, so V y will be minus V0 sin omega g t minus E by B. Okay. So, if you have this, you can also say, okay, so V y plus E by B will be minus V0 sin omega g t, and that is completely understandable from this equation as well. You see this one. Okay. So, if you have this equation and this equation, so you can actually from this equation you can also calculate y, and what will be that? So, y will be something very interesting. So, y will be equal to minus V0 by omega g. So, sign will be cos with a minus sign. So, it will be actually become plus cos omega g t minus E by B t plus y0. So, y minus y0 will be equal to V0 by omega g cos omega g t minus E by B t. Okay. So, you see this is another equation which will be of our use. So, I mean this one is simply, so if you say x minus x0 is this one, but for y now we have not like this. Okay. So, we have a trigonometric component, but another component which is linear with t. Okay. And this one actually gives us a motion where this, so you see that in the x direction, so x this x0. Okay. So, this x0 is actually not moving with time. So, x minus x0 is this. We can actually say, okay, so my x minus x0 will be simply equal to V0 by omega g sin omega g times t. Okay. I have y minus y plus minus y0 minus E by B t, which is equal to V0 by omega g cos omega g t. I can write like this as well. Okay. And then I can say, I can call this one as y0 prime. So, I can now say x minus x0 square plus y minus y0 prime square will be equal to V0 square by omega g square, or which looks like a circle. Okay. So, in an xy plane this looks like a circle, but we have to take caution that the center, okay, the center of the circle is actually changing with time, and that is why the interpretation of such thing is that, let us say you have the direction. So, y is this, x is this, and z is inside. Okay. Then if there is no E by B thing, then simply you will have a circle in this plane perpendicular to this z, which is xy plane. You would have a circle, and this is the circle of the gyration. Okay. But here what happens? Here you do not have a circle. Every time your x0 and the circle would have a guiding center x0 y0. Now your guiding center changes, although this x0 never changes, but this y0 changes, and this is changes monotonically and linearly with time. So, you will actually have a motion like this in this plane, xy plane. Okay. So, that your guiding center will be changing with time, and this is the drift motion, and for our case this is actually E cross B drift motion. Okay. Why it is called E cross B drift motion? That is only because if you just see in this case, this is, I mean, when you write this V y. So, I mean, if I just why this name E cross B comes. So, actually if you write the component of the force over here, you will see just a minute. So, I mean even here you can see. So, just in case this one, okay. So, I mean drift, this is so this E cross B drift means, so this is actually gives a drift velocity which is proportional to, I mean, V E cross B and divided by B square, that exactly I want to show you. So, this V y double dot, you will see that there is a term which is E by B. Okay. So, this E by B actually if you want to understand, so this is the extra term which comes as a special velocity type of thing in this y component of the velocity, this one. Okay. Now, why this, what is this E cross B here? So, E by B. E by B is nothing but E B by B square, and our construction says B is along z direction, E is along x direction. So, if we do E cross B, simply this will be x cross z. So, this will be a minus, okay, E cross B, and you take, I mean you can actually say that you just do not take the minus, but you just say this is nothing but E cross B by B square and mod of that, this is E by B. Okay. And so, we can say that this V y double dot is equal to minus omega g square times V y plus some extra velocity type of term which is given by. So, of course, here you see that everything V y double dot, everything has a direction y cap, and if you do E cross B, it will also be plus minus y cap, okay, that depends. So, you can think of this term to be an extra drift term which is looking like this, and that is why this is called an E cross B drift motion. Okay. Now, that was the simplest case where you have one uniform electric field and one uniform magnetic field which are situated perpendicular to each other. Okay. Now, if you have an electric field which is slowly varying with time, then you will have other drift motion called polarization drift. If you have a magnetic field which is weakly varying in its magnitude in space, then you will have something another drift motion which is called as a gradient drift. If you have an inhomogeneity not in the magnitude, but in the shapes of the magnetic field lines, then we will have something called curvature drift. All these type of drift motions are super important in the study of plasma, especially when we are talking of the energization of plasma in ionospheric plasmas, when you are trying to understand different type of phenomena like the aurora formation and everything, and sometimes in the space plasmas where we are trying to understand why certain plasma is accelerated or getting energized, then this type of motion can sometimes explain several mysterious questions. Okay. So, that is why knowledge of this E cross B drift and other drifts as well are of pivotal importance in case of the understanding of classical motion of a single particle in a plasma. Okay. So, with that I wrap up this lecture. Thank you.